Today we're going to apply what we just learned about polarity for molecules through what's called intermolecular forces. Inter, that prefix means between. So we're looking at between molecule forces. If I just had like a bucket of water, I'm looking at what forces are at play between a water molecule and a water molecule. And as a result of their molecular polarity, they will act like kind of different forms of magnets, because we just saw that when something is polar as a molecule, that means it has a dipole or a separation of charge within that molecule. And as a result, it'll kind of have two poles, positive and negative end, that will act like magnets. So let's read through this, and then we're going to apply the polarity concept that we just worked on yesterday and Monday to then apply to our intermolecular forces, or sometimes we just call them IMFs. So when the charge of a molecule is separated, it's called a polar compound. Polarity causes the molecule to have a positive end and a negative end like a magnet. As a result, polar molecules become sticky to each other. These attractions between positive and negative ends of neighboring molecules are called intermolecular forces. The greater the separation of charge in the molecule, the more sticky its interactions with neighboring molecules become. There are three types of intermolecular forces that we are going to study. London dispersion force. Sometimes this is also called van der Waals force, but we're going to call it London dispersion, and you can shorten that to LDF. London dispersion forces are weak attractions that are caused by random separation of charge as electrons move around. So if you think about how electrons kind of shift and move throughout orbits, you might have a moment where there's more electrons on the right side than on the left, and for that one split second, you have a separation of charge, but then it changes again because the electrons keep moving. That's why it's weak, because it only lasts for a moment, but in that moment it does create kind of like a momentary dipole. So this can occur even in nonpolar molecules where there are nonpolar bonds or equal sharing, because the electrons are just kind of moving on their own, not so much because of the electronegativity of the atoms involved. A dipole-dipole force is an attraction caused by the separation of charge due to electronegativity differences. This happens when you have a dipole, right? A difference in electronegativity, so you have a separation of charge caused from kind of that bond dipole, where one atom is stronger than another, and you'll have a kind of a constant separation of charge. So that's going to be a stronger force of attraction between, because it's kind of like a permanent magnet. Our third type is called a hydrogen bond, and this is the strongest type of intermolecular force. It's a special kind of dipole-dipole force, so it is going to be caused by a polar molecule. However, this one is due to extreme electronegativity differences. So we have a very, very electronegative atom with one that's not so much. So hydrogen is our one that's not so much. And then our very, very electronegative atoms, you'll probably notice fluorine, that's our most electronegative, nitrogen, and oxygen. If you have hydrogen bonded to one of these three in a molecule, then you have an extreme electronegativity difference, which will cause a greater separation of charge and make this magnet, if you will, really, really strong. So our hydrogen bond is kind of that third tier of the strongest type of intermolecular force. Now, before we go on, I just want to differentiate between inter and intra. Intramolecular, INTRA, that means inside. Those are just bonds inside of a molecule. So if I had, let's say, water, my intramolecular forces are my bonds, my shared pairs, okay? So if you ever see that distinction that you're looking for inside of a molecule, those are intramolecular forces. And then if I have water to water, because our polarity is going to separate charge, making this my negative end and this my positive end. Let me draw another water so that we can do inter. if I have H2O like this, got my negative end and my positive end, then if I had another water, then it is going to put its positive end toward this negative and arrange itself like this, and these kind of intermolecular forces are going to be between different water molecules. Okay, so there's your difference between intramolecular bonds and intermolecular forces. As you can see, even how I drew them, intermolecular forces are not as strong and steady as bonds themselves are. So in our table, let's summarize what kind of intermolecular forces would be in the different types of molecules. So after we analyze a molecule for polarity, then we can list its intermolecular forces based on what we've just learned about them here. So if our compound is nonpolar, that means it only has London dispersion forces, those random movement of electrons. But random movement of electrons happens in every molecule, so that would also affect polar ones and our extreme polar. So LDF are actually in every single molecule, but it's the only intermolecular force that's present in a nonpolar compound. Moving on to polar, we have LDF kind of laying that foundation, and then the next one you might see is dipole-dipole, and I'm shortening these to show you what you'll see in some of the practice coming up. LDF, DD, and then HB will represent hydrogen bond. A regular polar bond or a polar molecule will not have the hydrogen aspect. That's our special one, which is our third distinction here. But remember, this is still polar, so it does have dipole-dipole at play as well. And then it has our hydrogen bonded to a nitrogen, oxygen, or fluorine. So that would be hydrogen bond. And you can kind of see how this tiers up, making our hydrogen bond the strongest, or our polar molecule with hydrogen bonded to nitrogen, oxygen, or fluorine. That's going to have the most interactions going on. And then we have nonpolar with the least. So for each of these examples, you are going to analyze the molecule for polarity the same way that we did in the examples earlier in the week. So you will find its shape and bond dipoles using electronegativity, and then use those to figure out, is this polar or nonpolar? Then from there, now you have one more step using this idea in our table to then assign which intermolecular forces are present. So let's do a couple of these together just to kind of get you started. Analyze the bond dipoles and molecular shape for the molecules, label them as polar or nonpolar, then circle the intermolecular forces that would occur with the given molecule. So first, let's do the shape. We have two bonding regions and one non-bonding region. This would be bent. Hopefully you're getting good at finding the shape by now. If not, make sure you have that chart available so you can quickly check yourself. Now let's do the electronegativity. We have a bond here between nitrogen and fluorine. That will point to fluorine as our more electronegative. And then sulfur and nitrogen. Nitrogen is more electronegative. So it looks like we're pulling to the left overall. So this would be polar with a separation of charge, negative over here, positive over here. Remember thinking about where those arrows are taking the electrons to separate them and cause a dipole. As a result of this polar compound, remember everything has LDF, so you could really just go ahead and circle LDF for all of them. And then we have dipole-dipole because it's polar. Now notice we do have nitrogen and fluorine, which are part of our hydrogen bond. However, it's not linked to a hydrogen, so we cannot say it's a hydrogen bond. So a couple of things I see students incorrectly label hydrogen bond is anytime there's a hydrogen, they assume hydrogen bond, but it has to be with one of these three partners. And the other one is what I just talked about, seeing the partners but no hydrogen and assuming it's a hydrogen bond. Make sure you have both components there. Let's do one more. We've got diatomic hydrogen. This is a linear molecule. No central atom, no bond dipoles here, so this is nonpolar. And that means LDF only. So that's the application of our polarity. So we're continuing finding if the molecule has a molecular dipole, remember that separation of charge. If it does, it's polar. And then identifying which intermolecular forces are present.